We are going to have an intense day of knowledge and wisdom, as Isaac Asimov wanted to us to have. So, the first session starts now, and the first speaker is Nir Ailon from the Technion. Nir received his PhD in 2006 from Princeton University, and then he joined the Institute for Advanced Study for a year as a postdoctoral member. He then worked as a researcher at Google Research for 2 years. Since 2010, he is serving as an assistant professor at the Technion Department of Computer Science. He's interested in high-dimensional statistics, dimensionality reduction techniques, learning theory, preference analysis, ranking, and clustering. His work has been recognized by a SIAM Outstanding Paper Award in 2012. And the topic of his talk today is Fast Johnson-Lindenstrauss, History, Recent and Progress, and Open Questions. So, Neil, please.
Thank you for inviting me and organizing this, this great day, and thank you all for coming. So, I'll be talking about a problem that I've been cracking at since my PhD, since toward the end of my PhD, around 2006. The purpose of this talk is to survey the progress that I made with other people and other people made without me throughout until today, and also I'll present a new result. So it's not just going to be a survey talk, there's actually going to be something new. Okay, so let me just begin. Okay, so the challenge is basically that of dimensionality reduction or an embedding problem, a geometric embedding problem in Euclidean space, the simplest geometry that we all know. So you're given a database, you call it big X, and it has big N points. In dimension are small n. This is call it the ambient dimensionality of your data. But you want to represent it in fewer dimension, call it K. K will be much smaller than N. Typically, call it the embedding dimension. You want to do it using a randomized linear mapping. It's not the only way to do it. You can see lots of literature about nonlinear approaches, but this is what I'm going to talk about. Of course, if it's linear, it has to be randomized. You'll see in a second why. And you want to have low distortion. What I mean by that? I mean that I want to preserve all the pairwise distances in this set, big X, to within some small error. In this case, it will be a multiplicative error of 1 plus epsilon, 1 minus epsilon. Okay, so this is the picture. Your point X, which is supposed to be red, is in Rn. You flip some coins, you come up with some matrix, you call it phi, and then you get a k-dimensional point, call it phi x. Okay, so why is this even possible? In fact, it was known to be possible way before any application was related to it. So if phi is just a projection onto a random k-dimensional subspace, so there's a natural measure over k-dimensional subspaces of n dimensions, and k is roughly log of the number of points divided by epsilon squared. I'm sure that all of you have seen this already. Then with high probability, say 0.99, or if you want, you can also get inverse polynomial in the size of x. For any pair of points in your database, the norm or the distance between x and y in the reduced space, okay, phi x minus phi y, which is phi x minus y by linearity, is at most 1 plus epsilon, the original distance, and at least 1 minus epsilon times the original distance. Of course, you have to multiply by some constant to make this true, because there's a square root k over n loss here. But up to some constants, this is true. Okay, so this is the drawing. These are your 3 points in high dimension. 3 dimensions here. You choose a random subspace, dimension 2. It's this thing that I hope you're seeing. You project, and this is your new database. Okay, and now you run your complicated algorithm, nearest neighbor, SVD, linear regression on this space instead of on the original space. Okay, so this relation between k, epsilon, n, big N, and small n, and the probability of success is optimal. Okay, so we kind of think of k equals log of the number of points over epsilon squared as the optimal embedding dimension for this type of guarantee. Okay, so we'll call it throughout optimal JL. Now, of course, computer scientists have picked up on this and they said, hey, I have this algorithm that runs in, has complexity that is exponential, maybe in the dimensionality of the data, so why don't I do this step? I'll lose some, some distortion, I'll lose some accuracy, and then I'll have a problem, the dimension of which is logarithmic in the number of points, so that's great. But people also looked at so-called database-friendly versions of JL, and they discovered via various proofs that pretty much all take advantage of something called sub-Gaussian distributions. If you take phi to be just a matrix full of randomness, say every element in the matrix is plus minus 1, Gaussian, then you'll get this guarantee. Maybe the constants will be different, but pretty much the same. The proof is also much simpler. Also, the implementation is simpler. It's still optimal with respect to the definition of optimality that I just gave, and the proof is easier. And for example, here's a MATLAB code that will give you a matrix full of random plus minus ones. Okay, so that's just one row. Okay, so this slide is about applications, but I'm writing theoretical applications because there's also practical applications. It's not, well, it's a bit of an oxymoron, but I think I'll say something about this in a second. So there's classic papers by Indik and Motwani, 98, Ostrovsky, Kushilevi, and Rabbani, 2000. And I studied these papers as a PhD students, and I had some questions to ask about them, and this was the beginning of this work, actually. So they wrote papers about nearest neighbor searching. In this work, the space requirement, and I assume you all know what nearest neighbor searching is. I'm not going to define it. So you have the number of points is large N, big N. Okay, so the space requirement for these papers, the pre-processing space that you need, is exponent of log N and epsilon to the minus 2. So it's polynomial in N if epsilon is fixed. Okay, it's not very, that's why I call it a theoretical application. It's not really something you would do if epsilon is 1 over 100, okay? Pre-processing time is also similar to that. And the query time, the time to return the closest neighbor, or approximate closest neighbor of a given query point, is the time it will take you to reduce the dimensionality of that point. In other words, multiplying by a random matrix, plus something really, really small, polylog number of points over epsilon squared, something like that. When I read this paper, it seemed to me very odd that the time to do the dimensional reduction, as we'll see soon, is actually the bottleneck of this time. So it's kind of weird because when we think of reduction as of reducing one problem to another problem, the process of reduction should actually not overwhelm the overall computational time. Okay, and here are some, I'll say, practical applications because I think people have actually implemented these and tested these things. So this dimensionality reduction, Euclidean dimensionality reduction, is a good way to sort of massage high-dimensional data before you do something really complicated. And by really complicated, I mean usually linear algebra, SVD, linear regression, also large margin classification for learning. And papers on the subject are by Sarlos. He's has a nice paper from 2007, Drinas and people, and Liberty and collaborators around 2007. And these things came after the first fast Johnson-Lindenstrauss result, which I'll show in a second. Blend and Pick is a MATLAB library developed by Avron et al. And they actually use some ideas I'll present here in this, this library for doing SVD and linear regression. So I'll just say that the theoretical applications, those that require space n to the 1 over epsilon squared, they were actually the initial engine or motivation for this work, while I think there are other more practical applications that benefited from it. So, I mean, you can say something about the course of or the engine of research from this example. Okay, so what is the complexity of doing this dimensional reduction? Okay, I claim that it overwhelms the algorithm of Indik-Matwani and Ostrovsky-Kushilevitz-Rabani. So it's just the size of the matrix, okay? By complexity, I mean the time it will take you to reduce one vector, the next query vector for nearest neighbor, if you want. Okay, and this is just because this matrix has no structure. It's just a bunch of plus minus ones or Gaussians, depending what flavor you want. This is also the memory you need. You need to store this matrix in memory. This is also the amount of randomness you need if you care about it. For this talk, I won't really care about it. And it overwhelms this algorithm I presented. Okay, so in 2006, I looked at this problem together with my advisor, Bernard Chazelle, and we came up with a faster way to do the same thing for a large regime of parameters. By parameters, I mean k, small n, big N, epsilon, probability of success, and all that. Okay, so the solution, or the alternative way to get JL, which I'll call throughout FJLT, fast Johnson-Lindenstrauss transform, and this is take one. There'll be 3.5 takes. So you take your vector, you multiply it by a random diagonal matrix where you have plus minus 1 on each diagonal element. Multiply that by an Adamard, Walsh-Adamard matrix, which you can think of as a Fourier transform. Okay, it's a Fourier transform, not necessarily the one you study in the textbooks, but it is a Fourier transform. I'll call it H. You could also use a regular Fourier transform if you want. And then you multiply the resulting vector, which is so far just a rotation of your original vector, right? These matrices are orthogonal. Okay, we didn't lose anything in metric information. You multiply that by a sparse matrix, okay? K by N, a dimensional reduction matrix, which is sparse. What is the required sparsity? Roughly, you can see here, it's roughly, maybe this will work. Yes, K cubed non-zeros in this matrix you need in order to make this work. So the running time is K cubed plus N log N. That's the time to perform the Fourier transform. It will beat the, say, classic Johnson-Lindenstrauss k times n bound for k at most square root of n. For this k, you roughly get n to the 3/2 for both algorithms. You need to work a bit to understand why it's better for a very small k, but I won't get into that right now. You need to know a little trick here. But the important thing to take away from this slide or from this take one is that you get order of n log n running time for k at most cubic root of n. Okay? And somehow you believe, for reasons of, I don't know, maybe elegance, or maybe because it's so related to Fourier transform, you believe that this is the optimal you can do. Okay? So now the goal is to get order of n log n, but for larger k's, for larger embedding dimensions. Okay? What was the proof technique? So what you do is you look at a point in your database, and you see what happens to the point when you multiply it by the diagonal and the Fourier transform. And it turns out that its infinity norm, the largest in absolute value coordinate, cannot be too high. It can be something like that. This means that you rule out vectors that look like this. Okay, vectors that look like this cannot have a low L infinity norm. So in other words, the information is dense. Okay, it's well spread among all coordinates and not hiding in just too few coordinates. And once you know that your data has this property with high probability, of course, then you can use a sparse matrix in order to do the original, in order to get JL. The grand total is diagonal, Fourier transform, sparse matrix. Matuszek also analyzes this transformation and shows some related lower bounds to this. Very nice paper. The main probabilistic techniques used were really the ones that you study, say, in a first course in randomized algorithm. We would use tail bounds, Hefting and Chernoff, and maybe something related to chi-square, but not more complicated than that. Okay. Take two came 1 year later with my colleague and good friend IDO Liberty, and it works for k up to n to the half square root of n minus some tax. Okay, so this gamma can be as small as you want. For example, it works for k up to n to the 0.4999. Okay, and then this gamma is 0.0001, something like that. Okay? So it's starting to look more complicated, but the underlying ideas are pretty simple. You do this randomized Adamar transform, randomized Fourier transform, which is you take a diagonal plus minus 1 matrix, a random one, multiply it by a Fourier transform, and you repeat it a number of times, which is linear in 1 over gamma. So gamma was this tax that you paid, the slack you have from 0.5 in this exponent. And finally, you multiply by a dimension reduction matrix, a k by n matrix, which is deterministic. I won't say much about it. It's deterministic, and it's a non-trivial choice of rows from the Fourier transform. Okay, it's a deterministic subsampling. It's not a sampling, but it's deterministic. But it's a deterministic subset or submatrix of the Fourier transform, and it comes from an error-correcting code. Okay. So the running time, as you can see, is order of n log n for fixed gamma. Okay, so it works up to k equals, say, n to the 0.49. You get running time order of n log n. And what's the proof technique? I can say very little about it. Instead of looking at the L infinity norm that was used in the first analysis, you look at the L4 norm. And then there's this bootstrapping argument that goes roughly like this. Why do we multiply this vector x so many times by this combination of Fourier and random diagonal? So it turns out that if you look at the L4 norm of your vector after you do this random Fourier, it's at most the original L4 norm times some decay d to the minus gamma. That's why you need gamma to be greater than 0, so that this will actually decay, plus this term. So after so-and-so steps, you get that the L4 norm is roughly 1 over 4th square root of d. And this is what a quasi-random vector looks like. If you take a random Gaussian vector, say its L2 norm is 1, you normalize, then this will be its L4 norm. And that's good for Johnson-Lindenstrauss. Okay, and this final step is this error-correcting matrix, which I won't say more about it. The tail bounds that were used were a bit more complicated than the ones I showed earlier. Use Talleyrand bound for vector-valued Rademacher random variables. So what's that? If you have a random variable that looks like this, random sign combination of vectors, of a fixed collection of vectors, each one of these plus minus is a random bit, random coin flip. And you look at some norm of this random variable. So the probability that this random variable deviates from its median by more than any t is greater than 0, is like a Gaussian with standard deviation sigma, where sigma is some operator norm of the matrix which you get by stacking these vectors, v1 through vn, next to each other. Okay, so this is the operator norm you care about in order to control the tail of this random variable. And that's all we needed. For FJLT, we needed the operator norms of the Fourier matrix, because you see Fourier was part of the definition of this transformation. And these were already known via something called the Hausdorff-Young bounds for operator norms of Fourier transform. Okay, so this is classic stuff. Okay, so what happens above square root of n? So this is very frustrating because you've already used many, say, advanced classic tools like probability in Banach spaces and this harmonic analysis tool and error correcting code, but you still didn't get above square root of n. Okay, so what's going on here? So in parallel, there's another community, you can call it the compressed sensing community or the sparse recovery, sparse analysis community, and they looked at something called restricted isometry. So a matrix A has RIP, restricted isometry property, with parameters S and delta, if for all S sparse vectors X, there's low distortion, okay, in this sense. Very similar to JL, except that the set for which we want to have low distortion is fixed. It's just the set of sparse vectors. Okay, and this property is key to so-called universal recovery of sparse signals from few linear observations. And there's all these great ideas of a single pixel camera and compressed sensing, which is, I think Asimov would have probably been very excited about if he were alive. Okay, so for this theory, it's also important to have a fast RIP matrix. A matrix A with this property that you can apply to a vector quickly, because it will also imply that you can do fast recovery of sparse signals. So what's the connection between this JL and RIP? It seems like they're very much related. Okay, so this is a proof you can find in, I like the one in this paper by Baranuk et al. In 2008. So if you have a k by n Johnson-Lindenstrauss random matrix, then with high probability you have an RIP matrix with these parameters. Okay, and these are optimal parameters for RIP as well. So optimal JL with high probability gives you optimal RIP. The proof is just an epsilon net argument. Okay, you take the set of sparse vectors, you approximate it with a finite set, and then you apply the guarantees of Johnson-Lindenstrauss to show that you approximately embed this set. So that's an easy direction. Now, Rudolphson and Verschinen in 06 had an RIP construction that goes as follows. You take a Fourier transform, you flip some coins, and using the coins, you choose k random rows from this matrix, and that's your k by n RIP matrix with high probability. Except that you don't get, I think you probably don't remember, we had 1 log n factor here in the delta, and we're going to have log to the 4th of n here, the distortion parameter delta for RIP. So it's not optimal, but it's almost optimal, up to logarithmic factors. And this proof uses techniques also probability in Banach space. So I was interested in this paper. I took a look with my colleague, IDO, and we pretty much adapted this proof in order to get JL. And how did we do it? We took the exact same construction, except that we added no other than the random diagonal. What else would you do to convert that into a Johnson-Lindenstrauss transform, giving everything we've known so far? So you take this RIP construction, you add a random diagonal. Running time is order of n log n using the fast Fourier transform. And the proof technique is just adaptation of Rudolphson and Verschinen's result. Of course, we inherit the slight sacrifice in the guarantee. It's no longer JL optimal, because instead of 1 log of the size of the database, we have log to the 4th. And this is inherited from their proof technique. But we also, I guess, weren't very smart, and we also lost something in the dependence on the distortion. So instead of log n, say, to the 4th over epsilon squared, we get over epsilon to the 4th. Okay, it was still interesting. But then came Kramer and Ward, 2011, and they said, you know what, why don't we try to be more ambitious? We know that the JL to RIP direction is very easy. Let's try to prove a more general direction, more general deduction from RIP to JL. Is it true that every RIP matrix, which just knows how to preserve sparse vectors, can be converted into a JL matrix, which it can preserve any finite set of vectors? Okay, that seems like a more ambitious thing to do. And they actually showed that it's true. They show that if you have an RIP matrix and you precondition it, they call it with a random plus minus 1 diagonal, then you get a JL matrix. Okay, and this is the connection between the parameters. You need the sparsity here to be log of the size of the database, and delta from RIP is the epsilon from JL, and this gives you, with high probability, a JL matrix. Notice that this approach can never give you an optimal JL, because the RIP construction requires an extra log n in the first place. Okay, so if you want to get JL from RIP, you know that you will always lose 1 log of n. But it's a very, very neat result. And if you combine this result with Rudolphson and Verschinen's result, okay, then you get something stronger than what I could show with IDO Liberty. Basically, you get rid of the epsilon to the minus 4. You get the almost optimal result from Rudolphson and Verschinen, which means that there's epsilon to the minus 2, not epsilon to the minus 4. And maybe there's there's a game here with the log n's I won't get into. But you get Johnson-Lindenstrauss with log 4th n over epsilon squared. Running time order of n log n, no restriction on the embedding dimension k for any k. Now this is, I'll call this take 4. Okay, the proof techniques use so-called Rademacher chaos of degree 2. This is also actually a classic result by Hanson and Wright. I think it's from the 70s. It's a very nice result to teach in advanced probability class. I won't go into the details. How much time do you have?
15 minutes.
Oh, actually, I do have time. I've been going fast. Okay, so what's going on here? You have this RIP matrix, already denoted by R, okay? And you have this random diagonal, which I'll call D. And you want to ask what it does in terms of Euclidean norm, this transformation, for a vector. From your database, call it X. So take an S-sparse vector. Actually, you don't want an S-sparse vector. We're proving Johnson-Lindenstrauss, not RIP. Okay, so take a vector from your database X, and you look at the squared L2 norm of this transformation applied to your vector. Okay, so this is what it looks like once you open the parentheses. Now, where's the randomness here? It comes from this diagonal. Okay. Now, you can sort of assume for reasons of symmetry that this diagonal matrix is independent of this diagonal matrix, even though it's the same thing. Okay, this symmetrization argument. And then this random variable looks like this. You have the sum of the ith diagonal element times the jth diagonal element times some number mij, which you can read from this expression. Okay, it depends on X and on the RIP matrix. Now, this random variable, the probability that it exceeds t, for any real number t, is at most exponent of, so you have these two terms, t squared over the Frobenius norm of the matrix M. Okay, this is the Gaussian part of this random variable. And t over the spectral norm of the matrix M. This is the exponential part of this random variable. Okay, so this is a classic result, like I said, by Hanson and Wright. It's not very difficult to prove if you assume that these random variables are Gaussians. Because if that's what you assume, if these d's were Gaussians and not binary, a plus minus 1, then you can always diagonalize this matrix M, assume it's symmetric. So you can diagonalize it. And then you just get something that looks like a chi-square random variable. Okay, so this proof is actually not very difficult. Very nice to teach in class. And then you bound these norms, the Frobenius and the spectral norm of this matrix M, using the RIP property of this matrix R, which define the matrix M. Okay, so the proof is very technical. Most of the ideas, I mean, this is the main hammer in this proof. And I recommend this paper very much. So what is the picture right now? We have JL, and we have restricted isometry, and we have this bidirectional connection, almost equivalence. This direction is efficient in the sense that if you have an optimal JL construction, which is randomized, then with high probability you're going to get an optimal RIP matrix. Okay, you lose nothing. This direction is a bit more complicated. You precondition your RIP matrix with a random diagonal, and then you lose a factor of log n in the embedding dimension. You always lose a factor. You'll never get optimality for JL from RIP optimality. And that's actually quite clear. So in this sense, we think of JL as being more difficult than RIP. And it's actually quite intuitive because JL tries to preserve any database, any finite set of points with high probability. Okay, whereas RIP just wants to preserve one collection of points, and these are the sparse vectors. Okay, so it's not very surprising that you lose something from this direction. Okay, so RIP is easier. Okay, so if it's easier, let's take a step back and let's recall the take two of FGLT. Okay, so in that slide, in take two, we applied this repeated so-called random Fourier transform, which is the Fourier times the random diagonal, to our vector before doing something a bit more complicated with the error correcting code and all that. Okay, and that's how we got JL. Okay, so what happens if I only want RIP, which we know is easier? Okay, what happens if you do this HD, 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 HD process, and all you care about is whether or not you get an RIP matrix? You get something better. Okay, so this is this recent work I promised. And it's joined with Olga Raud from very recently. So the first result that we have is, okay, we still have the restriction on K. We couldn't get rid of it. But the first result is kind of very elegant. So for K at most cubic root of n, if you do this thing twice, okay, it's actually dH now. It doesn't really matter. It's dH, dH. Another Fourier transform. Finally, so far no dimension reduction. There's no RIP yet. Take any deterministic selection of K rows from the resulting matrix. Deterministic. You don't have to flip coins. Take the first K, take the last K, take the middle K, whatever you want. Okay? Arbitrary deterministic. So this transformation has optimal RIP parameters for any sparsity at most K over log n. Okay, this actually has to be this connection. Okay. I'll just mention that the only known constructions of optimal RIP matrices are randomized. Okay, nobody knows how to do deterministic optimal RIP matrices. Okay. So in fact, you can compare this result with the FGLT take 1, which worked also up to cubic root of n, except that there we needed a much more complicated selection matrix. We needed this matrix that had K cubed non-zeros. Here you just have a matrix which has K non-zeros, and it's deterministic, whereas there we needed something randomized. Okay, so that's you can call it a slight improvement. I don't know if it's a real improvement, but this is the transformation that we showed. So you need 3 Fourier transform and 2 random diagonals in order to get this result. The second result is more interesting. So for a given matrix, okay, we want our matrix to have the RIP, a restricted isometry property for some regime of parameters. So given an attempt for such a matrix, let's say it's not yet final, let's see how close it is to having RIP. So say the delta S of A is the infimum over all possible distortion parameters such that A has RIP with that parameter. Okay? Or in other words, the maximal distortion of an S-sparse vector by this matrix A. Okay? Let's say this is what you have so far. Okay, we need the same. Unfortunately, we could not break this this barrier, so you're at most square root of n minus, most that plus tax or minus tax. Now take your next attempt, call it A prime, to be your matrix A preconditioned by twice the transformation DH, diagonal Adamard Fourier, diagonal Fourier. Okay, so what is the lemma? If you do that, then the expected RIP, best RIP distortion parameter that you have for A prime is at most a constant less than 1 times the parameter you had for your previous draft plus this is what you want to have at the end. Okay? Okay, so you have an exponential decay in this parameter every time you apply this random transformation. Okay, so what is the conclusion from this? Okay, this is the bootstrap. Okay, so you're using the RIP of your previous version in order to get a better RIP for your next version. So the conclusion is that if you start with a matrix A, a k by n reduction, dimension reduction matrix, I mean RIP matrix, which is a type of dimension reduction, being anything reasonable, for example, just take k rows which are norm 1 and orthogonal to each other. Okay? It'll have pretty bad RIP parameters, but you can start with that. And then apply this double DH transformation a number of times. This is the first one. This is the last one. The number of times is roughly 1 over gamma, like previously. Then with high probability, this has optimal RIP parameters. And these are the parameters. This is the optimal parameters you can get here. Okay, now, the truth is you could have gotten this guarantee as far as the parameters with FGLT take 2. Didn't get anything new. But arguably, this matrix A, which you start with, can be anything you want, anything as silly as you want, as long as it's not, something stupid like, I don't know, if you have 2 identical rows, it's not going to work. But almost anything you want, and definitely not an error-correcting code, which is really hard to implement. So you can say this is more database-friendly if you want. Okay, so what is the proof technique? So here we needed, I guess, the most advanced tail inequalities for this, let's say, for this theory so far. So this is your vector here, which is sparse. You want to prove RIP. This is the previous draft, and then you precondition X with this transformation, and you apply your previous draft. This random variable, it's vector valued, and it's called a vector valued Rademacher chaos of degree 2. Okay, what's the definition of this animal? So you sum over ij, I from this matrix, j from this matrix, product of 2 random signs, call them alpha I from here, beta j from here, and some vector vij, which you sort of need to read from this definition. From this. Okay, you can define this vector. But it's a random sum of a matrix of vectors. Okay, for each ij, we have a vector. And you're taking a random sum of those with one sign coming from the I index and the other sign coming from the j index. Okay? So this gives rise to a 3-dimensional tensor. It's a matrix of vectors, if you want. Okay? And Talleyrand recently proved tails of such random variables, the norms of these random variables, and we care about the Euclidean norm here, using 2 tensor norms, sigma and sigma prime, and you have something that looks similar to Hanson right, except that it's for this tensor and not for a matrix. This is going to be very similar to the Frobenius norm, and this is going to be very similar to the spectral norm, but not exactly. Sigma prime, which takes the role of the spectral norm, but it's for a tensor, is defined as the supremum over 2 unit vectors, alpha and beta. You stick them in the diagonal instead of the random plus minus 1, and you look at the Euclidean norm of the same quadratic form that we defined earlier, quadratic form over vectors, not over scalars. And you take the supremum of that. That's the first norm you need here. So how do you bound this norm? Okay, so X is an S-sparse vector. This is a diagonal matrix with some unit norm vector beta on the diagonal, and this is the same with alpha. So let's go step by step. You have this vector X. Let's assume it has Euclidean norm 1. Okay. It's S-sparse, so its L1 norm is at most square root of S. Okay, this is the bound on its Euclidean norm. Now you multiply it by a Fourier transform. Each element in the matrix of Fourier transform is at most 1 over square root n in absolute value. So it means that the L infinity norm of the resulting vector is at most this times 1 over square root n. But the Fourier transform is also an isometry in Euclidean space, so you get the same L2 bound. Now you multiply this by a random, by diagonal matrix with some Euclidean unit norm vector on the diagonal. So by two applications, I guess, of Holder inequality, one is Cauchy-Schwarz, another is L infinity times, well, you can do the math, but you'll get that the L1 norm of this vector, this is Cauchy-Schwarz, is at most 1, and the L2 norm of this vector is exactly the L infinity norm of the previous one. And now you repeat these two steps again. In the end, you get that the L2 norm of this vector is at most 1 over square root n, and its L1 norm is at most square root s times that thing. Why is this connection important? Because a vector that has this connection, that the L1 norm is at most square root s times its L2 norm, looks in some very strong sense like an S-sparse vector. It's not S-sparse, but it's very close to being S-sparse. So then I can use the RIP of A of the previous draft in order to bound the L2 norm of this. And this is this bootstrap coming here again. Okay, so here I explain, I had one more. Okay, I'm explaining why one application of DH wouldn't work here. Here I'm explaining what it means to be an almost an S-sparse vector. I won't do that. I'll just mention two open problems and some more recent work. So why does this repeated HD technique fail so miserably for k above square root n? In fact, it fails a little bit below square root n. Okay, why is that? Okay, so it is quite clear to me that, say, if you apply this random transformation exponentially many times, your vector would look like a completely random vector, say a random Gaussian vector. And for such a vector, you can do JL just by choosing the first k coordinates. It doesn't matter, okay? But our proof techniques don't even give that for k greater than square root n. So obviously, there are some ideas out there that we need to know about, okay? If anybody's interested in an open question, this is one of them. Open problem 2. So is order of n log n, this was like the challenge that we set to ourselves. This was the bar. When we reach this challenge in terms of running time, or the time to apply our transformation to a vector, we said success. So is this really the best you can hope for? So this is a very simple consequence of take 1 of JL. Proving a lower bound would imply lower bounds for Fourier transform. And for those who know about this problem, you know that you don't mess with this problem unless you're already tenured. Okay? And I just want to mention some more recent related results. Nelson and Price, I think, improved the result by Kramer and Ward by shaving off one. There was log to the 4th n. They shaved off one of those very recently. And Nelson and Jelani Nelson and Daniel Kane also have interesting things to say about something called the sparse JL, and I really recommend for those who are interested in the subject to read this work.
Thank you. Just a tiny question. At some point you used the L4 norm. I didn't understand what property was of that specific norm that gave you what you wanted.
The reason we had L4 was, so we needed to bound the norm of some matrix, which this matrix was built both by the Fourier transform and the input vector, and they were sort of entangled. In order to disentangle them, you needed to apply Cauchy-Schwarz, which, let's say you have a sum of xi squared, yi squared, then that'll give you the L4 norm of x times the L4 norm of y. That was the way to separate the dependence on the Fourier transform and of your input matrix. And once you did that, you just used standard bounds of operator norms of Fourier transform, which is called Hausdorff-Young, to finish the proof in two lines. So it came from Cauchy-Schwarz on squared variables.